How's everyone doing today? Hope everyone's doing well. All right, let's get some water in the flask, shall we? Here we go. Just some water from my tap. Hope everyone's doing all right. Let's see what happens here. That's probably high enough. Got that little stir bar going. Oh yeah, there's our vortex. A beautiful vortex. Let's try some universal indicator, baby. Let's try some universal indicator. See what happens here. All right, and it goes. The first squirt starts off green. That's shifting to a little bit of a blue color. Look at how it just stays in the middle of the vortex. I love that. Absolutely love that. Let's add a little bit more. You see how the material I'm adding stays in the center of the vortex. That's, of course, because the eye of the vortex is low pressure. That material is going to tend to stay there until it hits the bottom stir bar and then gets pushed out along the sides. It's just an interesting little stream there. Let's add one more squirt. And we can check our pH here. What's our pH doing? I don't know. We got to check with our pH scale. All right. I'm going to try to plug in a light here. Give me a second. Should have had this going. Here we go. Let's pop this. Oh, I can't do that, huh? Well, it's good. Well, I got a plug here. Here we go. Put that one in. Put this light on. There we go. A little extra light for us so we can see the pH scale. Okay, sorry about that. Let's shine this over here. See what's happening. Okay. There's our pH scale. It's like a pH 7, maybe a little higher, maybe pH 8. What do you think? I'm thinking that's like a pH 7, maybe 7, a little higher than 7. It's got a little blue tint to it. All right, let's add a drop of acid. See what happens. Here we go. In goes a drop of acid. You might notice a bit of a red color. And then look at this yellow at the bottom. Sure enough. Oh, and it's getting red. It's getting red, baby. Let's add another drop. So you'll notice as I'm adding acid, of course, there's a red color developing. It's because the pH is dropping. How you doing there, Sibus? Good to have you there. So yeah, now it's like pH 3, right? Because I've been adding acid. When you add acid, the pH drops. I'm going to add some base. Should neutralize that acid. If it perfectly, well, that's like a pH, maybe a little bit between 3 and 4, because that's got an orange tint to it. Let me add just a little bit more acid, see if we can't get this to go down to pH 3. Like 3 more drops. There we go. We'll shift that reddish, excuse me, that orange color to more red. Thank you there, feelings. Appreciate that. I'm now going to add a drop of sodium hydroxide to the mix. Here we go, baby. Let's see what happens. This should raise the pH. And if it gets perfectly neutral, it'll be green. Let's add one drop here. Let's add 2. Boop. There's 2 drops. And get a little rainbow action there, huh? All the colors of the rainbow as the acid and base react with each other and neutralize. It looks like we're ending up right around pH 7. It looks like I have neutralized the system. Yeah, right around pH 7. Let's continue to add drops of base. You'll see what happens as I add base. There's another drop of base. And now we're all the way to like pH 10. That happened pretty quick. The base that I use is a bit more concentrated than the acid. See, we're up here at the like pH 9 or 10. Sorry, there's like pH 10 is like a purple color. All right, now we're going to start adding acid. The acid that I'm adding is hydrochloric acid. Same acid that's found in your stomach. It's just this stuff is like 100 to 1,000 times more concentrated. So hundreds of times more concentrated. Let's start adding drops of acid. In goes the hydrochloric acid. You can see me adding up here at the top. There's 1 drop, 2 drop, 3 drop, 4 drop, 5 drop. Let's see what happens. If you look carefully, you might see that red line in the middle of the vortex. And oh, there it is. We got a little rainbow action. That's really cool. And I think I've added just about enough acid to neutralize the base, because now it's green. Green is the neutral color. I'm going to keep adding acid. There's another drop, another drop, another drop. There's 3 more drops, 4 more drops, 5 more drops, 6 more drops. That's kind of looking reddish to me. I think we've got down to the lowest end of the pH scale that this indicator shows. It's called universal indicator. You can see we're down there at like pH 3. All right, I'm going to add a drop of sodium hydroxide, see if we can get a rainbow flash. Then I think I'm going to try a different experiment. Here we go. 1 drop of the base. Give me the rainbow, baby. Come on, baby. Give me the rainbow. Quick, another drop. I think we got it, folks. I think we got all the colors in one flash. Pretty close, pretty close. Beautiful, beautiful. Now it's neutralized. Let me add a little bit of acid to get it back down. We'll try to get that rainbow again. I'm going to turn the stir speed up a bit. All right, baby, come on now. Come on now. Give me that 1 drop. 1 drop of base. See if we can get that rainbow color. In it goes. Try another drop. In that one goes. I see all the likes. I appreciate those, folks. Keep them coming. Keep them coming. Very cool. Very cool. All right, let's add another drop. Put the emoji heart of the emoji heart color that you'd like to see. If you'd like to see me generate. Right now we're about like pH 8 or 9. pH 8 or 9 is where we're at. I say not like pH 8. I'll keep adding some acid to get that pH down now. A few drops there. Beautiful colors. All right, baby. Let's add some sodium hydroxide. See if we can't generate the rainbow. Come on now. Here we go. Let's add a drop of base and see what happens. Boom! Give it to me. Come on now. Come on, give me the rainbow. I missed it. Let me try again. Another drop. There we go. Ah, having trouble today, man. I'm having trouble generating the rainbow today. Come on now. We can do this. We can do this. That was kind of cool. Beautiful colors. So all I'm doing is I'm adding either acid or base to water that contains universal indicator. Universal indicator is also known as rainbow indicator. Oh, you got to be kidding me. You're a local hugger wugger. We got a tornado meteorologist in the chat. That's kind of cool. What I've got added to this water is universal indicator. It displays these colors at different pH values. Here at 10, that's a little bit of a water error there. That should all be violet. All right, I'm going to add 2 drops of sodium hydroxide base. See if we can't get this thing to show all the colors of the rainbow at once. 1, 2, let's see what happens. Oh, man, not enough. Here we go. 1 more drop. Come on, baby. Come on, baby. There it is. Little flash of the rainbow. Come on now. Ah. Hey, let's try another experiment. Let's do something different. Here we go. We're going to try something else. I'm going to take this off. We're going to try a different experiment. So what I'm going to do is I'm going to take some water. All right? I can turn this off. And to this water, I'm going to add another fluid called acetone. And we're going to see if the acetone and the water mix with one another. So let me go ahead and get my acetone out. And then we can see if the two mix. All right, so let me get this top off. So there's just water in here. It's just water from my tap. All right, and now I'm going to add some acetone. Oh, I don't have acetone. Well, that's no good. My can's empty. Do I have any? I guess we're not doing this experiment today unless I find some Let's find some alcohol around here. That would suck. But fortunately, I got other experiments ready to roll. Ah, here we go. Got a little. That's not going to be enough. Sure isn't. Well, we got to take that experiment off the table. Sorry about that, folks. I thought I had some acetone, and I don't. Curses. Curses. That's okay. We'll do some other experiments. I got them ready. Here's what we're going to do. I got a bunch of different waters we're going to test. We're going to test Icelandic water. We're going to test Evian water. Or Avion, I don't know how to say it. We're going to test Aquafina water. What else are we going to test? I got a few more brands here. Ah! Today is not my day. Today is not my day. We're going to test some Aquafina water. What else are we testing? Some Dasani. And what's this kind? Ice Mountain. Got some Ice Mountain. Yeah. And I have some Dasani. We got all kinds of water we're going to test. All right. Here we go. I got Icelandic. I got Evian. I got Aquafina. We can get another one on here. We're going to test some Dasani water. All these types of water. Let me put these back here so I can get a couple up front. We're also going to test Ice Mountain. And I think I have one more brand back here. I do. I have some Essentia water. So I figured it might be fun to test all these for pH and dissolved mineral content. Hello there, Aiden Pickles. What would happen if I added a surfactant? Hello there, Circuit. I don't know, man. Added a surfactant to the spin. You know, we could do that later. That'll be another experiment we can do today if we got the time. So here's what we're going to do. I'm going to add universal indicator to all these brands of water and more and just test their pH values to see if they're, like this. This one says, check it out right there, pH 8.4. Well, if that's the case, when I add universal indicator to this water, it should show like a aqua or a blue color, somewhere between aqua and blue. Let's see. We'll go ahead and test it. I'm going to add my universal indicator and see what happens. There we go. Icelandic water. Let's open this up. Fresh bottle of water. All right. I'm going to give it a nice squirt of universal indicator, which you will notice starts out a green color. In it goes. It looks like it's green at first, but then once it equilibrates with the fluid in the bottle, it should change. I'm guessing to like a aqua or a bluish color because, well, that's what the universal indicator says. Yeah, this is live, Giannis. Here we go. Look at that. Sure enough, we got like an aqua blue color. And that is consistent, like it says pH 8.4. And if we got a pH of around 8, we should see like this aqua color. And that fits pretty well. So it looks like Icelandic is indeed pH 8.4, just like it says on the bottle. We can test another one. Evian water. If you look on here, you see it says pH balance 7.2, says it right there. Well, if it's a pH 7, it indeed should show like a green color. Well, let's test this. We'll open this fresh bottle of Evian water up. I'm going to add some of the universal indicator and test its pH. Here we go, baby. Here we go, baby. Let me show you the universal indicator. There it is right there, okay? Get my bottle of universal. Out comes that nice green fluid. We're going to stick it in our bottle of Evian water. And is that green color going to stay? It should. Because it's saying it's pH 7. Give this baby a mix, huh? Mix that up. I don't know about you, that looks green to me. Yeah? I think that's looking green. So it looks like these companies are certainly, at least truthfully advertising. Let's check this one. This is another one. Essential water says that its pH is, sorry, it's hard to see that, pH 9.5 or higher. 9.5 or higher. So what color should that be? Let's find out. Let me get these guys off of here. So we're going to test Ascension next. Is pH higher pH better to drink or not? Not necessarily. All these water have a lot of water in it, and the water's job is to hydrate you. So all these waters are perfectly fine. Mostly the difference that you're going to notice is taste. And some people can't even notice a difference in taste in the water. Some can. So anyway, this says pH 9.5 or higher, so we should see like a blue or a violet color. Sorry, this I spilled something on here and it washed away the purple. But a pH 10 should be violet. So I'm expecting this color to look like this is like an aqua blue at pH 8. This should either be a deep blue or a violet color. All right, let's add our universal indicator to here. And the, pure water, perfectly pure water, which by the way is really hard to make, perfectly pure water would have a pH of 7. But, I can do some experiments to show you that's really difficult to achieve, perfectly pure water. Anyway, here comes a universal indicator. This should be a blue or a violet. Goes in looking kind of an aqua. There it is. Look at that shift to purple. What a beautiful shift to purple indeed. This does have a pH of, well, according to that universal indicator, that's going to have a pH of 9 or 10. Isn't that cool? I mean, these are all water perfectly safe to drink, but quite different pH values. This one has pH 8, roughly speaking. This one has pH 7, and this one is 9 or 10. All right, let's go to the next one, Aquafina. This one's interesting to test, very interesting to test, because you'll notice it says here that Aquafina is pure water. So this water is purified, and they don't add anything back. Now, if this water is perfectly pure, its pH should be 7, all right? If it's perfectly pure, its pH should be 7. So we're going to test this and see if it's perfectly pure, because if so, we should see a color sort of like this. We should see a green color, pH 7. That indicates neutral water. pH 7 is perfectly pure. So let's go ahead and see if this purified water has a pH of 7. I'll open up my bottle of Aquafina. I'm going to take my universal indicator, which should be green at pH 7. If this water's perfectly pure, squirt it in there. Sure looks green to start, but wait a minute. I see a shift to orange. What the heck? What the heck? I thought they said this water is pure water. Well, it can't be pure water. If it was pure water, its pH would be 7. But check it out. Its pH is like closer to 5, man. All right, maybe even 4. 4 or 5, somewhere in there. Yeah, that's a pretty low pH. So how can I get away with calling this pure water if it's clearly not pure? If it was pure, this should be 7, pH 7. What the heck is going on? Well, what all of these waters have been exposed to the air. Like, before bottling. Of course, most waters are going to be exposed to air in some way, shape, or form. It's very hard to keep something away from the air. That should make sense to you. And air contains a gas, not a lot of it, but it does contain carbon dioxide. And when carbon dioxide dissolves into water, it makes that water acidic. And that's why this water has an acidic pH, even though it has indeed been purified. I mean, Aquafina is purified through reverse osmosis. The carbon dioxide from the air that leaches into the water makes it slightly acidic. Now, what they'll do, because a lot of people don't like the taste of pure water, they will first purify the water, like this one. You'll see purified water, Dasani is purified water, and then they enhance with minerals for taste. So since a lot of people don't like the taste of pure water, they add minerals back. And let's see what the addition of those minerals do to purified water. If this is perfectly pure, with carbon dioxide in it, we're going to expect it to be orange. Let's see what the minerals do. I have a question here. Let me read this here. I read this as Chernobyl experiments. A uranotype. So I imagine a uranotype, that might be just like a maybe film that you develop with the X-ray, not the X-rays, but the radiation from uranium salts. Yeah, I wouldn't mess with that, but that's just me. Is that what you're talking about there, Frog Z? Okay, anyway, let's test our Dasani water. This stuff, remember, is purified, but then they add back. Okay, so the film is radioactive. That's kind of cool. How you doing there, Curb? Great to have you on board. We're going to test our Dasani water here. Got it. The film is made with uranyl nitrate. Interesting. So how's it work? I mean, how's the film developed? All right, let's add our universal indicator to the Dasani water and let's see what we get. Glad to have you on board, Curb, excuse me. All right, here we go, baby. Like Aquafina, this has been purified, but unlike Aquafina, minerals have been added back. And those minerals, well, it looks like those minerals make the water slightly less acidic. Check it out. That's more yellow, which indicates a pH 6, while this is like pH 4 or 5. So this has been purified with no minerals added back. This has been purified with minerals added back. Look at that. This is kind of interesting. Man, it'd be nice if we could have like, oh yeah, I know another kind of water we can add up here. We got almost all the colors of the rainbow. Check this out. Check this out. So we're missing red. We got orange. We got yellow. We got green. We got your blue. And we got your violet. So all we're missing is red. Pretty much like a normal photograph from what you've read. Same effect as using light to charge silver ions in the emulsion. But I can't imagine film that can expose itself being very useful. I can't either, man. You got it, Curb. Fitting colors for June. Happy Pride tomorrow for those that celebrate. Although other than making uranium glass, I don't have much else I can do. Oh, interesting. All right, let's make some water that is red. How would we do that? Well, you might remember I was telling you that when you add carbon dioxide to water, the water becomes acidic. So let's do that. We are going to do this in the following way. I am going to take some water from my tap right here. We're going to stick it in this bottle here. Let's stick it in this bottle here. This one's been open. All right, we're gonna take it. This bottle here. I'm gonna add some water from my tap to this. So in it goes. Water from my tap. And then I'm gonna add some universal indicator to it. So we get an idea of what the water from my tap is. Okay. Let's see what color this comes out to be. All right, ferrites, welcome aboard. We got a chemist in the chat here, folks. Chemistry professor Greg. Welcome aboard, Greg. Which are you? Organic? You do Gen Chem? You do both? You do a little P Chem, analytical? What do you teach out there, Greg? Right now, I'm currently doing a lot of general chemistry. I spent the most of my career doing general, analytical, and physical chemistry is what I taught at a smaller institution. I did that for years. Now at a larger institution where I just do large classes of general chemistry. Inorganic, crystallographer. Come on, baby. I love it. I guess you study ferrites is my guess. Why don't you tell us a little about those? Let the folks here in the chat know. We got a bona fide scientist here in the chat, which I'm loving. Maybe they can give us some insight into the kind of things that they do. So okay, we got some water from my tap. You can see its pH is like 7. Yeah, pH 7. Now what I'm going to do is I'm going to add some carbon dioxide to this water. All right, and I'm going to do that with my soda stream machine. So we'll back it off and let you see this. Check out my soda stream machine. Yeah, so, this thing, you just press this button and CO2 comes out. The only difference between science and playing with chemicals is writing down the results. Maybe Frogsy. I'd say science is a little more complicated than that, but I think it's a good start. It's a good, real good start. Okay, so let's put our bottle in here. Now, when I hit this button and you hear the hiss, oh, cool. So Greg is saying they know very little about ferrites. Real last name is Ference. And my research students named our group the Ferrites a couple decades ago. Cool, man. So you're probably just making a bunch of inorganic compounds, measuring the X-ray crystal structure of those and making new stuff. I'm hoping. I don't know if I'm hoping. I'm just wondering. I'm pretty sure you're supposed to hold the button on the bottom to make sure it doesn't fall off. Hey, all right, here's what I'm going to do. I'm going to give this up here at the top, I'm going to give this a press. Carbon dioxide is going to get bubbled into here. And watch what happens to our pH value, okay? Watch what happens. Just stick that under there. Anyway, here we go. Let me put that over there. It might get wet. Here we go. 1, 2, 3. CO2. Ah, look at that, baby. Come on now. That was orange. And that is red, baby. I told you I was going to make red. Carbon dioxide, when it dissolves in water, is acidic. Look at that. pH 3, man. Up here, look at the foam, though. The foam is like a different color. So you can see the foam. Oh, no, it's going up the top. Oh, man, this is going to overflow, but it's cool because you can see the foam has a lower pH than the stuff in the water. That's because the CO2 is escaping from the foam. So it's going to have a lower pH. Isn't that kind of cool? It is acidic. You're right, Curb. CO2 in water is acidic. Carbon dioxide is indeed an acid. It's an acid. It's a type of acid. There's different types of acid, different ways that chemists define them. CO2 is what's known as a Lewis acid. A Lewis acid. It also can technically be known as an Arrhenius acid, but I'm getting a little technical here. Let me go ahead and open this up. Hopefully it won't spray out all over. Yep, there we go. Look at that. I got all the colors of the rainbow. Come on now. Let's check it out. Let's review here before I set up another rainbow experiment. Because, tomorrow starts Pride. Look at this. I've got red. That's water with carbon dioxide in it. Then purified water that does not have carbon dioxide removed, that's going to be like a pH of like 4 or 5. Now, this has CO2 in it, and this has CO2 in it. Why is this less acidic than this? That's because I pumped in a crap ton of carbon dioxide into this, like a really high pressure. The pressure of carbon dioxide in the air is much lower, so this is just exposed to the air, so the CO2 that this gets is just from the air. So this is going to have a higher pH, lower acidity than something that I pumped a bunch into. All right. Okay, next thing is Dasani. That's where we got our yellow. So Dasani water. Kirk Baller, never thought they'd see a food grade mineral water, carbonated water machine being used for general chemistry. Yep, I use it for that, but I do not use it for drinking. So because I use that SodaStream machine for experiments, I don't use it for drinking. Beautiful, Greg. That's interesting, man. Lewis acid also makes the magic work in Crayola color wonder markers. Patricia, you know that. Absolutely. She's been hanging out on my channel. You know that to be true. I'm going to go ahead and seal this one up so that if it falls off, because I get excited, if that falls off, it'll be sealed. Okay, so we got red, orange, yellow. How did I get green? Well, green, that just came from Evian water. Evian water is pH 7. So we got red, orange, yellow, green. This is pH 8. So that one's blue, Icelandic. And then finally, our essential water is our violet. So we got all the colors of the rainbow. Isn't that cool? Red, orange, yellow, green, blue, and violet. Just from different brands of water or water that was made in different ways. I think this might be a video. I think I might make a video out of this someday. There's a knockoff SodaStream machine that has replaceable, removable heads so you can wash it. It doesn't specify you can only carbonate water. UWO Labs carbonated cheese. He made carbonated cheese soup. That's crazy, man. That's cool, man. Carbonated cheese soup. Oh, I wonder how that tasted. Let's do another rainbow experiment. We'll do one more here. And then I think I might stream on TikTok for a bit. You got it, man. You got it, Patricia. All right, last experiment for today. And then I'll flip the camera around and talk to you guys for a little bit. I'd like to do that at the end. All right, let's try this one. I'm going to put a flask on here. We'll focus in on the flask. I like this one. You guys are going to love this experiment. This is a great one. It's a great one. Of course, I got to pour in some of my water. In goes the water. It's just water from my tap. All right, let's get my stir bar going. Get in there, baby. Start spinning. Start spinning. One cool thing with carbonated, wait, I missed some stuff. Here we go. In Gen Chem, Greg likes to pick a big and small mark and get 2 samples of water, one pure and one buffered, both pH green. Guess Tommy Technetium knows where this is going. Yeah, that's fun. Add a little drop of acid to one, turns red. Add a little drop of acid to the other, the color stays green. I love that. It's a great thing to show students. It blows their minds, man. One cool thing with carbonated water, there are actually, I'm pretty sure, whole bathhouses that let you swim in carbonated water. That would be crazy. Swimming in soda, huh? Science book I had as a kid had an experiment in it to make invisible ink using iodine and cornstarch. Interesting. It's a beautiful day. That's right, Brett. Glad to have you on board. Oh, I see. Ah, Greg, I like it, man. I like it. Student blows with the air in the straw and it goes red quick. The other one, I love it. You get a big dude. That's great. I didn't see that one coming. Yeah, it does, man. The camera rate does make it look like the stir bar is just like twitching. Yep. Color change. All right, here we go. What I'm going to do now is, of course, I'm going to add a little universal indicator to this so we know what pH my tap water is, and then we're going to start messing around. So here we go. In goes a big old squirt. That's like green, yeah. So that's like pH neutral. I also want you to notice that you can see through the solution. The solution is transparent. So the solution is clear, and it's also green. It's transparent and green. How do we know it's transparent? You can see my hand back here, right? You can see my fingers. You know, the light's bending stuff, but still, I can see through this. Okay. Now what I'm going to do is I'm going to add some milk of magnesia to this. All right, milk of magnesia. Milk of magnesia has some solid particles in it. It's not transparent. It's opaque. Watch. I'll pull it up into this. You see that? You can't see through the white stuff. So one of Kirk's favorites is from the experiment list. It's just using metals with some flames, colorful flames. Copper is beautiful, beautiful green copper flame. So this is magnesium hydroxide, actually solid particles of magnesium hydroxide. You can't see through this because of the solid particles that are in here. I'm going to pour this in, see what happens to our color. Notice it is now, you can't see through the solution. That's because there's a bunch of solid particles that have been suspended in here. So this is no longer transparent, and that's because there have been some solid particles of magnesium hydroxide that are now suspended into our mixture. And you'll notice the pH, it's looking like it's gone up, like it's like a pH 8 right now. I'm going to let that set. The reason why the pH has gone up is because a little bit of the magnesium hydroxide dissolves. And when that magnesium hydroxide dissolves, it makes the solution basic. We'll let that go just a bit more. Milk of magnesia bugs you, but you understand nobody wants to eat magnesium hydroxide, right? But milk of magnesia, yeah, maybe I'll do that. Maybe I'll do that. Look at that nice color. Let's see. Try to shine that on there so we can see it. It's like a It's like a bluish violet. Yeah, it's a little hard to see, but you can kind of see that we got like a bluish violet color. Let me see if this light off helps. Yeah, maybe a little bit. Most people say that basic stuff tastes bitter. Sour stuff tastes sour. Or excuse me, acid stuff tastes sour. Now what I'm going to do, so now, like this is like a blue or violet color. So the pH is very high because a little bit of that solid dissolved, making it basic. All right, so we're up here. I'm now going to add acid to this, and the acid will be dissolved, but the solid, it looks violet to me now, the solid magnesium hydroxide that remains will neutralize the acid that I add. So when I add the acid, we're going to see it go red, but then as the solid neutralizes the acid that I add, we should see the color get pulled back somewhere along the line, all right? All right, here we go. Let's add, I'm going to add like 3 drops of acid, see what happens. Here we go, maybe 4. 1, 2, 3, 4, 5. So it goes red from the acid. It's still magnesium hydroxide in there. I know that because it's not transparent. And you can see it's shifted all the way back to yellow at this point. And as the solid that's in there continues to react with the acid that I've added, that should shift back maybe to blue or maybe green or maybe even violet. Come on, man. It looks like we may be stuck. There we go. We're getting we're shifting to a little bit of green. I added quite a bit of acid, which is why this is taking so long. Let's add another drop. No, let's wait. All right, here we go. We're back to neutral. So I'm going to add another drop of acid. Turns red, yeah. But because there's some solid left, it immediately goes to yellow and slowly shifts back to the neutral green. If I let this sit long enough, it may go all the way back to blue or violet. But I'm just going to keep doing this because there's only so much solid in here. Every time I add some of the acid, some of this solid reacts with it. And when the solid reacts with it, it dissolves. So when this goes transparent again, all the magnesium hydroxide will be gone. Here, let me add another drop of acid. Let's do 1. There it goes. See, it turns red, and the solid there immediately neutralizes it. Here we go. Let's add another drop. Boom. Red, orange, yellow, and green. Let's add another drop. Let's do 2. 1, 2. Red, orange, yellow, and slowly to green, like pea green, and then kind of a green. Let's add 2 more drops. Here we go. 1, 2. Red. It's going a little slower. Orange, yellow, green. Brett, what'd you get your PhD in? Here we go. Let's add 2 more drops. Boom, boom. Red, orange, yellow, green. Pharmacology. I remember, Brett. It took me, yeah, I remember. I remember talking to you about that. Check it out, though. As I've continued to add acid, you can tell this is. Come on, servant. Servant says, it sent me $5. I really appreciate that. It's not necessary. It is helpful. It's helpful to buy materials for these experiments. Servant says, this makes me miss jar testing for water treatment. I love titrating pH and alkalinity before adding coagulants and watching the flock form. Servant, I wish I could do some experiments with it. You're talking about some things I'm not sure I've tried before. So it'd be interesting to do those experiments. The flock. What the heck is flock? Tell me that again. Is that just like the suspended solids? Because we got some suspended solids in here for sure. That's why this thing is not like it's getting a little more transparent, but you can see it's not quite transparent yet. That's because there are still solid particles in here. So I'm going to add. Awesome, servant. Thanks for teaching me. Thanks for keeping me up to speed. That's what I thought it was, but when you do general chemistry like me, there's just so much to know and so much to forget. Here, let's add 2 more drops. 1, 2. Oh man, that didn't even get to red. Ah, gotcha. Biology word. Then what I'm doing is I've added some milk of magnesia to this flask. Milk of magnesia is a white solid. Those solid particles are suspended in here, which is why this flask, the contents of this flask are opaque. And then I add acid to it. So I'm going to add like 2 drops of acid. The acid changes the pH to red, well, to like pH 3, but the solid that's in there, it neutralizes it. So that's why you're seeing the color change. So when I add the acid, it drops to pH 3 or 4, depending on, how much gets in there, how quickly. And then the solid that's left over, it neutralizes the acid that I added. So now we're back to green, and I'm going to add a couple more drops of acid here. Here we go, 2 more drops. Boom, boom. If there's any solid left, we should see this red color get pulled back, and indeed it does. You see how it's getting a little less transparent, though? We're running out of the solid, folks. At some, thank you there, ferrites. Flocculent is precipitate. At some point, the solid will be gone, and when I add this stuff, it'll stay red. Let's add 2 more drops. Boom, boom. Yes, frogs. Here, I'll show you the chemical equation. I'll write it down here. So the chemical equation is going to look like this. The formula for magnesium hydroxide is this. MgOH2, and I put that little less there because it's solid, and those are the little solid particles that we can't see. Now I'm going to add some hydrochloric acid, HCl, 2 drops. Boom, boom. It's going to go red plus 2 HCl. I'm going to write AQ like this. So 2 hydrochloric acid. I write this AQ behind it because this stuff is dissolved in water. All right. Anything that's dissolved in water, you put this little AQ behind it. And this stuff doesn't block the light. Solids will. This would be transparent. This is not transparent. These 2 things are going to react. Here we go. I'm going to draw that little arrow to indicate they react. And what do they make? They make 2 molecules of water. So it just becomes part of the water. And it becomes dissolved minerals, magnesium chloride. See? So this and this, these are both transparent. So this is a salt that's dissolved. And that's why slowly over time, as I add acid to the cloudy stuff in the flask, it's slowly getting more and more transparent over time. It's still not perfectly transparent, so if I add some more, we should see the color shift back. It's going to go red, and the solid that's there is going to pull it back to neutral. We can keep going. It's still not transparent. 2 more drops. 1, 2. Down the side it goes. There's not as much solid present, so it's going to take a little longer, but we're back to yellow. There's enough solid there, and it's still a little bit opaque. It's not perfectly transparent. So I'm thinking if I add another drop, it's still going to change the color back. Oh yeah. Brett, I have not. Have I done? I don't think I've ever done the red cabbage. I've done blueberries. I've done all sorts of acid-base indicators, but I've never done red cabbage. Isn't that funny? Isn't that something? All right, let's do 2 more drops here. I don't know why. I should put it on the list. That's still not transparent. That's coming back. Yep, there it is. Amen, Frogsy. All right, let's do 2 more drops here. Boom, boom. 2 more drops. It's still not transparent. That's going to come back. I agree. I'm live there, Ganumba. I am live. Welcome aboard. I agree, Patricia, that the vortex, we are seeing more detail as the solid is getting dissolved through the chemical reaction. Let's add 2 more drops. We're getting close. 1, 2. I'm going to add 3. If you can get your hands on some liquid nitrogen, you should totally make a video where you freeze. Oh, I've done that, Kirk Baller. Seriously, check out my shorts videos. Check out a bunch of my stuff. You'll see a ton of experiments that I do with liquid nitrogen. That's coming back. That's orange. Yeah, I agree, Brett. I've done that a couple of times, but I definitely stopped doing it when I learned how bad it was. Poor man's liquid nitrogen. Yep, you see it's orange, so we know there's some solid left. It's looking quite transparent, but not perfectly transparent. I can still see some flocculent. That's our word of the day. I can still see some flocculent or solid particles in there. Yeah, Curb Baller, I've done some experiments with liquid oxygen. I've had 2 more drops here. I still think I see some solid in there. That's coming back to orange. Do I have some? Do I have soap down here? I do. We're gonna do the glitter. We're gonna do the glitter today. This may be it, folks. I think I may have got rid of all. I should say reacted away all of the solid. I think we're back. Although no, that's looking kind of orange. That's looking orange. I think maybe the next 2 drops will get us there. Do you see it's slightly orange now rather than red? I think so. I think there was enough solid in there that the acid I added was reacted away. What do you think? Put an orange heart in the chat if you think it looks orange. Put a red heart in the chat if you think it still looks red. To my eye, that looks orange. I just want to make sure we're in general agreement here. Let's see what folks think. I see an orange heart, so that's 2 votes. Me and Curb Baller for orange. Ah, nice. I love the observation there, Patricia. Patricia says, look at the stir bar. That's helping you see whether, yeah, the stir bar is still a little hidden. That's funny, Frog Z. Servant says it's orange. Let's add like, I don't know. Let's add like, all right, it's orange. Let's add a few more drops of acid here. See if we can't get this stuff transparent. I gave it a good old squirt. I think that might be it. Look at that stir bar. That stir bar is nice and visible. I did there, Brett. I gave it a good old squirt. I think we're back. What I'm going to do is I'm going to set this off to the side. I'm going to set this. We'll just set this off to the side, okay? Set her off to the side. I'm gonna do a vortex experiment here. Hope I got enough water. I may have to go get some. Let's do a vortex experiment because this is fun, man. Ha! Thank you there, ferrites. Metastable technetium, baby. Best wishes, man. Best wishes. Good luck with your classes and your research. Hope to see you around in the chat sometime again. All right. Let's get our stir bar in here. Come on, baby. It won't fall off of the magnet. Let me try again. Here we go. All right. All right, let's get some water in here. Pour this one in. You guys are going to like this. We're going to do the glitter tornado today. The glitter tornado. You guys seen the glitter tornado before? Then we'll call it good. All right, in goes a bunch more water. Get that rolling. I think that's going to work nice. Yeah? All right. Trip out on the free energy with a stir plate and spark plug and a magnet. All right. Look at that vortex, folks. Let me turn this light off so we can see what's going on in there a little better. All right, I am going to add glitter to this vortex. What do you think is going to happen when I add glitter to the vortex? Just curious. Drop your hypothesis into the chat of what you think is going to happen when I pour some glitter into this vortex. Let's do, I don't know. I don't know what color to do. I got to read these comments here. Hold on a sec. What are people saying that is going to happen when I put glitter into the vortex? It'll stop. It'll contaminate everything in your life, and you'll never be able to get rid of it. Put a CD in a microwave. Brett says it wants blue. Wodio says red. Centrifugal force will send it out to the sides of the glass. Wodio says orange. Curveballer says I will find the glitter in my hair. So I've got blue. I got blue glitter. Here, I'll turn on this light so you can see it, and then I'll turn it back off so we can focus on the vortex again. You guys aren't going to believe this. There's some blue glitter. Here's some green glitter. And here's some orange glitter. Put your emoji heart in the chat to tell me which one you want. I don't see any votes for orange, blue, or green at this point, but I want to start counting here. Come on now. So I got a vote for blue. I got a vote for green. I got a vote for blue. I can vote for green. Lots of votes for blue. There's a vote for orange. All the colors. Why not? Why not, man? Let's do it. So I think I saw most of the votes for blue, so we're going to do blue first. Here we go, baby. All right. Watch it up here at the top. Don't miss it. Up here, up at the top, I'm going to add the glitter. I'm just going to start sprinkling it in. Here we go. In goes the glitter. In goes the glitter. In goes the glitter, baby. Look at that, man. It stays on the inside of the vortex. You also get these things, I like to call them glitter bombs. Yeah, you see those happen as well. What the heck? Why does this happen? Why does it happen that the glitter kind of, it coats the inside of the vortex, and yet, it doesn't really seem to spread out along all of the mixture. Isn't that interesting? Hydrophobic glitter, baby. You got it, servant. That's exactly right. Surface tension is another way you can describe this. I think they're basically equivalent. Yeah, isn't that cool? Hydrophobic glitter. So glitter, I'm going to add a little bit more. Glitter's hydrophobic. So it basically does not, quote unquote, want to be mixed into the water. And that's why it's going to coat the inside. Look at that, man. That's interesting. It's kind of like the orange glitter likes the inside better. Or maybe it's just that the blue glitter kind of matches the color of the water better, and that's why it looks like it. Look at that. It's like a two-color vortex, man. Let's add a little bit of green and see what happens. I'm so glad you guys said let's try this. You know, maybe it's just this. Maybe I think this is it. The glitter that I've added, it pushes the older glitter down. That's what it looks like is going on. Isn't that cool, man? It like coats the inside of the vortex. Come on, baby! I like orange. Really pops. Look at that orange. Look at that. And these glitter bombs here. So these are bubbles, and the inside surface of those bubbles, those are also coated with the glitter as well. Look at those things, man. It looks like some kind of monster. Isn't that beautiful? Look at it. Okay, now what we're going to do is we're going to add a drop of detergent. And what detergent does is it allows hydrophobic substances, which glitter is, to mix with water. Yeah? You guys want to watch this a little while longer? Because as soon as I add this drop of detergent, likewise there, Wodio. You guys ready for the detergent? Yep, it'll break the surface tension for sure, K23. K23 favors the surface tension explanation, which works. Magnetic glitter, what a great idea. Soap time, baby. All right, Mickey's ready. Here we go, folks, up here at the top. I'm going to add the drop of glitter or a drop of detergent. Watch what happens. One little drop, 1, 2, and it goes. It's working its way. Let's add another drop. I think I need to add a little more. I don't think I've hit the critical micelle concentration. We're going to add another drop here. Just pour it in. There we go. There it is. The glitter is now being dispersed throughout the water. Very slowly. It's taken some time. But as it's working its way through the vortex, the glitter that I have added is now getting dispersed throughout the entire flask of water. Isn't that beautiful? Isn't that cool, man? It looks like noise. It does. But a little bit more. Just a bit more. See if you can get that glitter out of the middle. And now, just so you can see, I'm going to add some orange glitter to the top. Watch what happens here. Forbidden drink. Okay, here we go. I'm going to add this glitter here. Man, that's staying in the vortex. That I did not expect to see that, but I don't think it's going to stay there. You can see it. You can see it's getting flushed out of the vortex because the detergent's been added. Let's watch that again. That's cool, man, because it stays in. Look at this. It stays in the vortex. There it goes. I just added it. It's in the vortex, but because detergent has been added, it slowly weasels its way out of the vortex and into the water. Isn't that cool? Very cool. The video keeps buffering. That's what it looks like. The vortex is glitterophobic. I hear you, Kirk Baller. I hear you. All right. I'm going to turn the camera around. So if you don't want to see an old man in his basement, now's the time to get on out of here. I'm going to go ahead and answer some questions in the chat so you can see me face to face. You like that kind of thing. Thanks for being with me today. I agree, Frogs. We got to work on the lighting. Hey, everybody. How are we doing out there today? Had a great time doing experiments with you today. Had a good time. That was fun. We did a lot of cool stuff. We did a bunch of different stuff. That was fun. Brett, thank you, man. Great having you on board. Thanks for joining the conversation, talking with us all. It's always great to get different people chiming in so we can talk about a lot of different things. I gotta turn all these lights on, make myself look, this old man look a little better. What's the molecule on your shirt, servant? What do you think, baby? You know what it is? I think maybe you can figure it out. Yeah, it was Dawn dish detergent, Patricia. That's what I used. That's all I used. Dawn dish detergent, glitter. That was fun, K23. Yeah, hey man, it's just fun being together. It's fun doing science together. Aromatic something. It's it's found in fungi, a special type of fungi. I think you'll figure out the rest. Not THC. But you think, hey, Kirk, come on now. Appreciate that. Buy some of those experiment equipment. Thank you, man. Sent me €2. Wonderful, Kirk. Thank you. Curb, excuse me. Thank you so much. It's not caffeine. Servant got it. It's not THC. There you go. K23. K23's got it. Check out K23's comment. You'll figure it out. Today, Patricia. Today, I've been thinking about some stuff today, so I thought I'd put that shirt on. The best chemicals and benzene rings. I don't know about that. I think my favorite chemicals are water and carbon dioxide. And I don't think water and carbon dioxide don't have benzene rings, right? But hey, you know what? I told you my two favorite molecules, water and carbon dioxide. Tell me yours. I'd love to hear what your favorite molecules are. I also like this one. This one's pretty cool. This one's pretty awesome. We got some ethanol. There you go, K23. Yeah. A lot of folks like some ethanol. No benzene ring in ethanol. No benzene ring in this molecule. Isn't hydric acid the stuff people drown in usually? If you inhale only 2 ounces of the stuff, I don't know what hydric acid is. Somebody help me out. Your favorite hydroxyl hydrocarbon. There you go. Neuroplasticity from fungus is definitely awesome, man. Uh, so, servant, does it make your brain more plastic? Is that true? I don't know. I Plastic resins. Really, Curb? Curb likes the plastic resins. Interesting. Oh yeah, benzene PU for sure. Dihydrogen monoxide, hydrated oxygen. Indeed, I gotcha. I got you, Frog Z. Well, hey, we've been at this an hour. That's enough for me. An hour of me looking at the screen. That's enough. I start to go a little brain dead after about an hour. So thanks for hanging out, folks. I had a good time with you all today. I actually had a blast. And I want to tell you this. I tell people this, when I was in college, it became my dream to do science experiments for people. So I got to do that today, and you're a part of that. So thank you for helping this old man make his dreams come true. And I mean that. I really do mean that. Had a great time doing science experiments. I always do. Always enjoy it. People bring a lot of energy, teach me stuff, and I just love it. Let me just look through these last few comments, and I'm gonna call it quits for the day. All right, thanks, K23. Appreciate that. Thank you for the subscription. I really do appreciate that. Wonderful. I hope I don't disappoint. All right, guys and gals and others, great having you on board today. We're going to see you next week around this time. Thanks for getting me to do some experiments I don't normally do. And, pay attention to the beauty of the universe. It's always around you. And think about the science behind it, too, because that makes things a little more beautiful. So long, folks.